Okay, today let's see how to find the eigenvectors of a 3 by 3 matrix. We have seen how to find the eigenvalues of a 3 by 3 matrix, and I use this same equation. Now, the task is to find the eigenvector of this matrix. We have actually created a detailed lesson on how to find the eigenvalue, which is what you must first get before you can find the eigenvector. Or I'll go through finding the eigenvalues first, then I'll find the eigenvector. But if you're interested in just the eigenvectors, you can skip the video. I'll place timestamps in the description below for you to access eigenvectors directly. Now, the first thing, like we said in our first lesson, that remember that our AX is the same thing as lambda x. Now, if AX is the same thing as lambda x, we agreed that A minus lambda into I, the determinant of this, which is our characteristics equation, is equals to 0. Now, based on this premise, we're able to find the eigenvalues. Now, that is, if I have, this is my matrix A, here is minus 1, 0, 4, 2, 1, minus 1, here is 0, not minus 0. Now, minus the identity matrix multiplied by my lambda. I've shown how to derive this in our lesson. You can check the description below. I'll place a link to that lesson. Now here is 0, 0, and here is lambda. Now obviously this the determinant of this is what we're looking for to make our characteristics equation. Now this will translate to 2 minus lambda. Here will be 0, 1. Here is minus 1, 4, minus 1, minus 1, 2. So this is 4 minus lambda, 2, and here will be negative lambda is equals to 0. Now, by the time you solve this, I've shown how to solve this in details. You should come to lambda to be equals to 1, 2, and 3. These are the values of lambda you will get. Now, if you need the solution to this, please do check the description below. There's a link to that lesson. Now, when we get lambda to be equals to 1, 2, and 3, from here we can now begin to find the eigenvectors when lambda is equals to 1. Remember we said Ax is the same thing as lambda times x. That is, we're picking the root matrix 2, 0, 1, minus 1, 4, minus 1, minus 1, 2, 0, into x. Our x is x1, x2, and x3. Now we're saying that this is the same thing as lambda. When lambda is 1, this will be scalar 1 multiplying this vector x1, x2, and x3. Now our eigenvector is actually, this is our eigenvector here. This is what we are now looking for. Now, how do we go about this? Well, I've just redrawn, I've just rewritten the matrix equation. Now to find my x1, I want to turn this to a proper equation. So it becomes 2x1, 0 times x2, that's 0, plus x3 is equals to x1, minus 1 x1 plus 4 x2 minus x3 is equals to x2. And the third equation b minus x1 plus 2x2, it is 0 again, is equals to x3. Now, obviously, from my equation 1, let's start with equation 1. Let's call this equation 1. From equation 1, I can now deduce that, let's call it like terms, 2x1 minus x1 plus x3 is equals to 0. So that x1 plus x3 is equals to 0. So that conclusively, x1 is equals to negative x3. Now, if you look at it this way, we have seen from here now that x1 from this equation will equals to negative x3, and putting it back in this equation, we have that our x2 equals to 0. So we know that for every one of x1, for every one of x1, we have a negative x3. So that if x1 now is equals to k, we'll be saying that x2 will be equals to 0 and x3 will be equals to minus k. Now I can write my Eigenvector, first Eigenvector to now be 1, 0, and minus 1. But let's see when lambda is equals to 2. Let's see when lambda is equals to 2. When lambda is equals to 2, what I'm just doing is, in place of this 1 here, I'm replacing 1 with 2. So I still have the same set of equations, but I'll be multiplying my quotient with 2. So that my 2x1 plus x3 now be equals to 2x1, and minus x1 plus 4x2 minus x3 will be equals to 2x2, and my minus x1 plus 2x2 will be equals to 2x3. Now, if you look at, let's start this again, equation 1. From that equation 1, we can deduce that 2x1 plus x3 minus 2x1 is equals to 0. Obviously, 2x1 minus 2x1 becomes 0. Then I'm left with x3 equals to 0. So automatically, x3 from this equation is equals to 0. But we don't have a value for, we don't have a relationship or a value for x1 or x2 yet. So let's plug it into, let's plug it into equation 2. Equation 2. Now, plugging it into equation 2 becomes minus x1 plus 4x2 is equals to 2x2. You know, we've said x3 is equals to 0. So this becomes minus x1 plus 4x2, I like to collect like terms, minus 2x2 is equals to 0. Now this is minus x1 plus 2x2 is equals to 0. Automatically or obviously, x1 is equals to 2x2. Now we can conclude and pick our relationship here, because we have x3 to be equals to 0. We have x1 to be equals to 2x2, which tells me that for every one of x2, I'll have 2 of x1. That is, if x2 is equals to a, for x1, I will have 2a. So I can rewrite my vector this way. For the second vector, I can write it this way, as this will be 2k, that's 2, 1, and 0. Now let's look at the last eigenvector. When lambda, let's look at the last eigenvector. When lambda is equals to 3. Now when lambda is equals to 3, we're picking the same sets of equations. We're saying 2x1 plus x3 is equals to 3x1, and minus x1 plus 4x2 minus x3 is equals to 3x2, and lastly minus x1 plus 2x2 is equals to 3x3. Now we said now we can see that from equation 1, let's pick our first equation 1, 2x1 plus x3 is equals to 3 x1, let's collect like terms. We'll say that 2x1 minus 3x1 plus x3 is equals to 0. So that this is minus x1 plus x3 is equals to 0. Obviously, x1 is equals to x3. Obviously, if x1 is equals to x3, what happens to x2? Let's derive a relationship for it from our second equation. Second equation says minus x1 plus 4x2 minus x3 is equals to 3x2. So we'll be saying that if x1 is equals to x3, in the place of x1, I can easily replace it with what? x3. This becomes x3, negative x3 plus 4x2. Let's collect like terms alongside. Minus 3x2 minus x3 is equals to 0. So that this becomes minus 2x3 plus x2 is equals to 0. So that x2 invariably is the same thing as 2x3. Now we've gotten that x3 is equals to x1, then we can derive a relationship for it. That is, for every one of x1, I have one of x3. And for every one of x3, I have two of what? I have, for every one of x2, I have two of x3. That is, x1 is equals to a. x2 will definitely be the same thing as 2a. And x3 will be the same thing as what? As a. So I can bring my eigenvector to be 1, 2, and 1. With this, I hope you've seen how to find eigenvalues and eigenvectors. Please, in case you're yet to subscribe to our channel, kindly hit the subscribe button. That way, you'll be telling YouTube you love what we're doing. Thank you, and see you in our next class.